this paper and in this talk, green energy are the systems and technologies that mitigate climate change by reducing carbon emissions while supporting long-term large-scale renewable energy. So we have quite substantial goals in terms of this reduction, and what we're primarily focused on in our group as part of the Imperial Rock Mechanics research group is in trying to put forward what we think is a role of geomechanics in de-risking some of these technologies. And of course, challenges relate to energy security. So how do we make sure that as we transition into renewable energies, we remain secure and we have a secure secure access to our energy provision over longer periods of time, so that we can balance out different changes in economy, geopolitics, etc. How do we make sure that we can store energy over longer periods of time? How can we do this efficiently, but also in a low carbon or carbon zero or carbon neutral manner, and so on? And how does that go together with the electrification of the chemical industry, the decarbonization of the cement industry, etc., right? So, and what we realize, as many other people in our field also realized, is that the subsurface actually has a huge role in trying to enable this. So geological batteries, for example, gigaton storage of CO2, storage of energy fuels like hydrogen, ammonia, storage of heat, both shallow and deep, low and high enthalpy, and then mining of minerals for renewables. It is all interlinked, all to do with the subsurface, and we try to understand, okay, what aspects of geomechanics need to be developed further so that we are in the best position possible. And we talk a little bit about numerical models and also lab experiments and so on, but in general we talk about the properties of what we understand of the subsurface and the uncertainties around those. And so we are quite focused on things like emphasizing the effect of heterogeneities and the effect of the uncertainties on property characterization and so on. So what is in general the role of geomechanics in these technologies? And the role of geomechanics really is to de-risk specific aspects of these technologies. Like, for example, will there be any mobilization of fluids in situ that we're not planning for? Will there be any leaks that may compromise drinking water, or will there be any induced seismicity? Will there be any subsidence, etc., etc.? The geomechanics has to do with lots of these different aspects. And as we are very acutely aware, this strongly depends, so our ability to say anything about the geomechanics of a site strongly depends on our understanding the characterization of the in situ properties of that site. What are the rock properties? What are the in situ stresses? What is the permeability? What is the Young's modulus, and so on? And we try to dive into these in a very systematic manner to try to understand, okay, what do we understand? What do we understand about these properties? Which of these properties are the most important to characterize, and how are we going about that? And we discuss in our paper stresses, elastic moduli, strength, permeability, and faults and fractures as our sort of bread and butter of geomechanics. This is like the input for our analysis at this for this type of analysis that we conduct, so the numerical modeling of these types of models, of these types of processes, and material properties and in situ conditions, right, which are really determining factors in the ability of these models to be predictive, or in a way conducive to some sort of ideal scenario mapping or understanding of what the constraints of our scenarios are. So we want to, in general, be able to predict behavior during the injection and withdrawal of fluids, as we have always wanted to do, but now with new challenges. Like, for example, now we might need to oscillate in our injection and withdrawal. We might need shorter periods of injection at much larger volumes. We might need our systems. So we talk here about nuclear waste disposal as well, because we find that even though it's not a fluid that is being injected, it is still a disruption to the subsurface that is conducive as well to understand the importance of geomechanics. And what can we say about enhancing permeability and controlling permeability in general? So for many years now, the geomechanics community has been studying how to control permeability, how to engineer permeability in the subsurface. How can we increase it under certain conditions, and then make sure that it remains low under other conditions? And shale gas production is a very good example of that. CO2 sequestration and cap rock integrity is a very good example of that too. But basically, we're moving towards engineering of the subsurface permeability, and and the role of numerical methods in this type of analysis is of course quite important, but numerical methods are only as valuable as the material properties, in situ properties, in situ conditions, etc., of the real site and how these apply there. Of course, we do a lot of parametric space analysis and this type of thing as well. But at the end of the day, if we want to be precise, we do need to have some real information about the site. So then the paper starts talking about these different factors. So subsurface stresses being the first one that we identify as important. I add here, I'm sure everybody knows what subsurface in situ stresses are, and that they're caused by the overburden and also the situational stresses, let's put it this way, of being underground at this whatever depth you are, and that you can make different assumptions about them, and so on. And we include this because it is extremely important to characterize in situ stresses or it is our finding over many years of numerical modeling that the characterization of in situ stresses remains extremely important in order for these numerical methods to be predictive. Young's modulus is another important, quite important property as well, that in many cases, again, is not properly characterized, especially for the type of rock that is interesting for renewable energy. So for example, cap rocks are very poorly characterized. So there is a huge volume of data for reservoirs, but perhaps not that much for cap rock. Actually, we did an in-depth study, and we found there was a huge difference here in characterization. Of course, we're working with public data. What companies then have as part of their asset characterization, that is for them to know, but we are talking here about what is in the public domain and what is being used in general to de-risk these processes and feed into government policy, for example, from the scientific point of view, coming from universities and research centers. So we know that Young's modulus increases with stress, so it displays hysteresis in cycles, decreases with temperature and water content, increases with applied stress, exhibits hysteresis during unloading and loading, decreases due to micro damage, and so on. So I don't add here all the different references, but what we tried to do in the paper was to try to identify what we thought were the most important and impactful papers that determined these specific sort of qualitative expressions of constraint on these properties, and try to put them all in one paper so that we could then go back to them later, and for also all our students and other related researchers to understand where we are getting these assumptions from. So we have that. There is a scarcity of cap rock data, as I was mentioning, and also as we go into deeper and deeper formations, again, some of the rocks are less and less characterized, even more so when we talk about other things like fractures and so on. So bulk and shear moduli, let me just check I'm doing. Bulk and shear moduli was another of our chosen properties. These are not everyone's favorite, but we added them here because they're quite important as well. They basically tell us what the resistance to hydrostatic compression is, and it's there are ways of approximating what they are as a function of the Young's modulus. But we stress that they need independent measurement, and and that we use these in numerical modeling, and they can also affect the types of predictions that we make in terms of the deformation of the cap rock, because at the end of the day, they're also controlling the rock response to pressure changes in storage and injection, and they play an integral role in understanding the behavior of geological and engineered processes. So we thought it's important to put this message out there as well. Poisson's ratio, again, was as well one of the factors that we were, or one of the material properties that we were looking at. Again, there are many studies looking at this, but we were looking at this sort of at the compound level. We were looking at different new advanced characterization techniques as well, using micro CT and analyzing so we're also looking at anisotropy of the rock, I should say, is very important, not only for shale rocks, but for clay stones and other types of low permeability rocks. And maybe depending at the scale at which you look at it, it's for different reasons. And there are different techniques that can be used to measure this anisotropy in the elastic properties at different scales, and there's still a lot of uncertainty about how to upscale these geomechanical properties. So again, upscaling is a theme, an ongoing theme in the paper and in the book as well, where we talk a lot about how there has been a huge effort in upscaling flow properties in the field, but that effort has not really been paralleled in geomechanics, and that's something that we foresee will start happening now. And there are a lot of papers coming out through the multiple journals that I'm involved in, trying to come up with different methods to upscale the different properties under different conditions. But of course, once you start taking into account that you have actually temperature, fluid pressure, and deformation changing at and displacement basically all changing at the same time, you need to characterize these types of properties for this changing parametric space. And then finally, but not least importantly, faults and fractures are extremely important, and we find more and more evidence that rocks behave differently when you have fractures in them, and they display different properties at different scales depending on how these cracks distribute, what their properties are. They affect permeability, they affect mechanics, they affect also temperature changes, and so on. And we are very focused in our group in understanding how fractures change and how their growth and interaction affect permeability. So I wrote with my colleagues and postdocs and PhD students a series of papers where we look at how permeability depends on not only on the presence of fractures, but in their actual structure. So actually, if we look at randomly generated fracture networks, they have inherently different permeability properties than fracture networks that have been generated using geomechanical principles, so actually following the geomechanical relationships, observing stresses and interaction effects, and so on. So these and the same is for aperture. So there's a huge effect on what you do with your apertures. If you define apertures as being a single value in your entire data set, or if you define your aperture to be mechanically dependent, or if you define the aperture as being something scale dependent, and so on, all will affect the probability and so on. And we've also looked into more recently into how fractures and heterogeneities affect faulting, and how this changes under dynamic settings as opposed to quasi-static settings. So we were looking sort of at slower evolving systems over many years, and now we're looking at dynamically evolving systems more recently. So after we talked about all these properties in the paper, and I would suggest it's a really good place to go and look at where all these constraints and assumptions are being referenced from. We then try to link that to the different green energy technologies. The first one and most obvious being carbon sequestration. We've known that geomechanics is important for carbon sequestration for many years. We know that the deformation of the cap rock is paramount. We don't want it to lose integrity. We don't want faults to reactivate. We don't want faults to leak. We don't want fractures to propagate between the reservoir and the cap rock. We don't know what will happen over very large periods of time. What happens if you lower the permeability through your CO2 sequestration of your reservoir and perhaps the lower part of your cap rock over many 20 or 30 years, and will that then eventually result in unstoppable fracture growth? We don't think so, but is it something that we can constrain from now, from the get-go, and can we do that to financially aid these projects so that their outlook is much better constrained? Geothermal energy is, again, extremely linked to geomechanical behavior as well, especially for systems where you have fractures. You may be using fractures to establish initial or enhance your permeability in situ, or you may have an existing fracture network. You may have a number of fractures. You may have a single huge fracture. You may have faults going through. You may be mining heat from a fault as well, like we do in the UK. So there are a lot of different options here, and you want to understand how you can control your system and constrain your system so that you decrease in as much as possible the risk of induced seismicity, leak of your drilling fluid, or, well, really your working fluid, and what different constraints this might have. Of course, thermal drift. What happens if you deplete the heat from your flow path, and what do you do about that? How can you prevent it? How can you slow it down? What are the different techniques? And of course, this is related to geomechanics because some of the permeability is being controlled by the relationship between the thermal strains and the apertures of the different fractures, and also the movement of the faults and so on. So we have some projects into geothermal energy looking at injection cycling challenges. So what happens if I want to inject use even shorter cycles than we are actually used to relying on, and what are the different stability risks that we're facing, and so on. Hydrogen storage and in general low density fluid storage is something that we've been looking at as well in a lot of detail over the last couple of years, especially because all of our work up to now has been showing that at least from the point of view of induced seismicity, this seems to be quite a safe technology. Now for the leak, that's a different can of worms, but of course, there are others looking at hydrogen storage in salt caverns and repurposed gas storage caverns, whereas what I was just mentioning was about the potential storage at large scale in porous media. And when we say hydrogen, we also sort of, by extension, think of ammonia, which is a slightly larger molecule, might be better as a candidate for, in a sense, hydrogen storage, and it might be something that starts happening as well, even in Europe. So nuclear waste disposal was one of the green technologies that we were considering. We did on purpose put this in here because we need to be able to handle this waste in a conscientious and sustainable manner. It is not something, it is part of our renewable future, and it is something that will have to happen at scale in all nuclear countries, and it is ongoing right now. So it is, and at the core, extremely related to all of these other technologies that we were talking about, not from the geological point of view in a sense, but rather from the numerical modeling point of view, because from the numerical modeling point of view, you are solving a very similar system. You don't have fluid circulating as injection through an injection well and being removed somewhere else, but you are looking at scenarios where you have sources of fluid migrating through the GDF or passing through the GDF, where you're looking at transport and so on, and you're looking at the effects of the thermal gradient of the waste canisters on the surrounding rock, and you're looking at how the rock behaves and interacts with other rock units and so on. So from the point of view, from the most sort of basic point of view of numerical modeling and so on, we are using the same technology. And what we have for many years strived to do in our group as well, or our vision has been that in reality we should be using the same simulator to look at all these properties, because it is basically the same physics. So that's what we're aiming for, and that's what we're doing, and that's what we're executing. Of course, as well, another of these, so this concludes, this is our fourth technology, right? But then we looked at, after looking at these four, we looked at four risks, or four challenges really, that are related to these different technologies in some way or another. And
I think we've just lost. Adriana, we've lost. I think we lost you there for a few minutes, and we've lost
you
your.
lose me for a couple of minutes. Oh my God. Okay.
No. It was really maybe just 1 minute maximum. It wasn't very long.
Okay, I was talking about subsidence, which is the most boring part anyway. So subsidence.
Can you reshare your screen, because the
oh, is it not sharing again anymore? Okay, wait a moment.
Okay, here. This is exactly where we were at, and you started with the fourth technology, and then you kind of dropped out. If that's a place you could continue from.
So did you wait 1 moment? Can you see my screen now? Did you see this slide, the nuclear waste disposal?
You started.
But then you lost.
It was this slide that you started. This is.
Okay. So the fourth technology that we incorporated was nuclear waste disposal. We incorporated it because even though it doesn't seem to be related to all of the other technologies that we were talking about before, actually from the point of view of the numerical modeling and the prediction, it is extremely related. So the types of geological characterization, the types of material property characterization, in situ properties, and on the other side, the type of equations that we're using to characterize the system are very similar. Even though we are not purposely injecting a fluid into the system, we are looking at scenarios where there is a source of fluid somewhere in the GDF, and there is migration of fluid in the rock unit where the waste is being disposed. And we're looking at the effects of temperature on deformation and on fluid flow, and we're looking at the different feedback mechanisms that then may or may not elevate the risk or affect the different safeguarding design decisions that are being made to design these tunnels. So in a sense, even though it looks or it may feel disjointed, actually for us it's extremely well jointed, and we use exactly the same simulation tools to look at all of the different technologies, or really at the rock deformation in these different four scenarios. And then we looked, so we did all the material properties to gather our understanding there. We looked at these four what we think are most relevant technologies, at least from our point of view at this very moment. And then we looked at four challenges that are common to those. The first of them being surface subsidence. Surface subsidence is, of course, due to compaction of some of the rock units above whatever site you are operating on, and of course the footprint of that compaction in the surface. And this creates a huge cost for the economy and affects social perception of these different technologies. So it's an extremely important aspect of the technology.
That's 5 minutes. That's 5 minutes.
5 minutes, okay. So let me just check my own. Okay. And of course, we have induced seismicity, which we have again focused quite significantly over the years. So what creates human-provoked seismic activity, and how can we try to prevent that and to reduce it and minimize it and so on. And we have an ongoing project funded by the UK government, looking at different aspects of induced seismicity and how the dynamics play an important role and how heterogeneities play an important role. But we found that it is quite important how the rock, what the rock characterization is. So if you look into fault reactivation and induced seismicity literature, and we did so quite extensively, there are only very few studies that actually look at the effect of rock properties into the actual reactivation of the faults. It's actually, most of the studies are looking at operational settings, maybe in situ stresses, and to some extent as well fault properties, but mainly really injection strategies, and not so much looking at what are the properties of the rocks that are around my faults, what are the properties of the rocks above my fault, and so on. So we have a project of which I'm the PI, where we look at everything from the characterization in the lab scale through of the rocks, of the faults, looking at heterogeneities, numerical modeling, also physics-based risk modeling, and social perception. So we look, and from that work, we've already identified, for example, that cascading events may be promoted by heterogeneity. So we're getting more and more evidence that heterogeneities actually might change the picture of induced seismicity, and this might be linked to why we are consistently unable controlling the movement of the fluid in the reservoir and beyond the reservoir, when we be able to control this.
Adriana,
yes.
Sorry, you just dropped out again. You just dropped out again, and that was on cascading events, and you were just finishing your thought on heterogeneities, and that's when you dropped out.
Can you still see my screen?
Yes, I can still see your screen.
That's good. Okay, so I was just finishing here with the fact that we, in our studies of the effects of heterogeneities on fault reactivation, we have already started to find that having heterogeneities on your fault changes the types of predictions that we were making before for homogeneous faults. So we anticipate that there will be substantial further learnings from understanding how heterogeneities in the faults affect induced seismicity. So for example, if my fault is going through a series of rock units of different compliances and different properties, how do these then affect my actual induced seismicity? And it's not only about the fault itself anymore, but understanding what the rock surrounding the fault is, which is from a geological point of view quite sensible. Then we also looked at fluid and contaminant leakage. Of course, this is a very important other aspect that is related, or challenge that is related to many of these different subsurface technologies. And leakage is, of course, in the eyes of the public, an immensely important problem, because they don't want their water to be contaminated, they don't want gases to reach the surface, etc., etc. So a lot of the leakage studies are really going into safety cases and reduction of risks. And all of these challenges feed into public perception. So it is extremely important when, not only when studying these problems, but also when explaining the risks associated to these geomechanical challenges, that we constrain them and that we phrase them in a way that the general public can interpret them for what they are, and that these are not inflated or exaggerated and so on. So we're really trying to make here an emphasis on how important this is. So for example, for our induced seismicity project, we have a whole work package that looks into translating the different learnings from our project into the correct phrasing and context, so that it is mostly beneficial to understanding what the risks of the different technologies are, what the understandings are, and so on, so that we really enable both the public and the government to feed into the regulatory process in the best way possible. And we think that it is that social perception in an indirect way, and we have a couple of papers on this, or pointing to this, is very related as well to geomechanical studies that discuss these technologies and the different issues around them. So finally, in the last couple of minutes, I'll just mention what we do, what we do actually in our day-to-day lives. We actually are developing, so I'm the lead of this tool, Imperial College Geomechanics Toolkit, that has existed for over a decade at Imperial, and it is focused on the numerical modeling of porothermal mechanical deformation of fractured and faulted subsurface rocks. And we have applied it to and validated it in a number of different contexts, so CO2 sequestration, but a lot of emphasis on fracture growth, and penetration, for example, of fractures into cap rocks, migration of thermal fronts, hydraulic fracturing, fracture networking, fracture network growth, geomechanically realistic fracture network growth under different conditions, always looking at it in a coupled manner. And recently we have been looking more closely at incorporating dynamic aspects into our simulations. So for example, looking at how faults deform and how that deformation is affected by heterogeneity. So these points here on these stains here on the fault are actually basically areas of higher friction as compared to the rest. And we also are always constantly looking at better ways to couple not only the THM, but also numerically how the THM affects aperture, how it interacts with contact and friction and growth. And so we have a paper that just came out in CMAME that discusses what the most up-to-date, fully coupled version of our simulator is implementing, and how we have found that actually by coupling these processes even further, our numerical systems become much more stable and also more accurate. So we're, even though it's more complicated to implement, it is, and to validate, we are finding that it is actually much more stable to look at a more coupled system. So instead of less coupling, we are advocating for more coupling, so as to be more faithful to the physical environment that we are trying to navigate. So conclusions, as you well know, as you already might suspect, geomechanics is really important. It's at the core of many of the goals that we have that are related to our green energy transition. So we need to expand CCS by 100 times, or those are the goals. Geothermal capacity quite substantially as well. Hydrogen storage goals are as well quite substantially for 2050. The construction of nuclear waste repositories all around the world, at least 5 to 10 operational by 2050, including in the UK. Induced seismicity, we need to learn to manage it below 2 and 4, keep it there and minimize the risks. And that's of leakage. That's it. And I hope this was somewhat useful to you all. Thank you.
Adriana, thank you so much for this far-reaching presentation, and it's great to see the work that you're doing in Imperial. Thank you for, and I think it was perfect close to our workshop today. So really happy about that. Thank you again. We have a question in the chat, and I have a couple of questions myself, but we'll go to the to Robert Gales. Hey Bob, how's it going? Glad you could join us. I'll read out your question. If you have any follow-up, I'll unmute you. A good presentation, Adriana. You mentioned subsidence. I've heard of this from production, not from injection. What is most lifting from injection encountered? Has there been induced seismicity out with production when subsidence occurs?
Okay, so this is mixing both subsidence and induced seismicity, right? So yes, subsidence is mainly observed when you are producing. But what we are thinking will happen or might happen in the future is that many of these technologies require cyclic injection production, right? And so you will have, oh, sorry, is that someone else? Sorry. So you might have some compaction if you don't manage your pore pressure correctly, right? And looking at subsidence is still an important component of that. Now, induced seismicity with production, yes. So I think induced seismicity is related to any relief, or can be related to any migration of flow in the subsurface, whether it's injection or production. It can be related to both, depending on the setting that you're looking at. So it is, I mean, what I presented is very generic. It is an attempt of bringing different things together and raising awareness about why geomechanics is worth investing in general, right? Why we should bother, not only numerically modeling these, but actually characterizing the system, because we can't characterize, we can't model it if we don't characterize it. I could have added like graphs and graphs showing this, but because the message is so long, I just use this approach. So I hope this tries to address this question.
I'm just looking at other questions. Maybe okay, I will take the opportunity now. I have a reflection and a question. The first one, I was really happy about you raising the lack of data in cap rocks. I think this was a very good statement to make. And you did mention, and then you caveated that is based on open, publicly available data, but it's not just publicly available data. It is pervasive. The overburden is by and large under characterized. That is the truth. We drill, the oil and gas industry drilled through the overburden to get to the reservoir. We did that in an optimal way at the time for our objectives, for a successful well objective, which was complete and produce hydrocarbons. So, the well objectives are very much aligned with data acquisition and thereby also knowledge. We will have had best practice, doing leak-off tests and doing all this in the overburden, etc. But our priority was always to get to the reservoir. So that was one reflection that I had. And the other was, I did see some of the estimates about 5 to 10 times the nuclear storage capacity required. I think it was the number. But I'm just curious, and the question is does that take into account the current increase in SMR activity and potential boom in nuclear energy for the future? I was just curious if your estimates take that into account.
No, so maybe I don't want anyone to misinterpret what I said. So we have one under construction right now, at least here in Europe, right, which is a Swedish site. By 2050, what this is saying is that we're likely to have 5 or more sites. I'm not saying that we will require more volume than what is assumed now. In fact, it is quite expected that Gen 4 reactors will be more efficient in terms of fuel and wastage, and that the decommissioning efforts will be relieved by it. But we have an amount of legacy waste that we do have to deal with, and it's not. I'm not saying by any means that there are any predictions that will increase significantly. In fact, if anything, it will, at the rate at which we're producing it will remain less or equal than what we have now. So
that's clear. Thank you for that. Really appreciate that. We've got a question from Nadir. Great presentation, Adriana. You rightly mentioned about scale effects on rock properties and requirement to upscale them. What are your best practices for both fractured carbonate reservoirs and unfractured reservoirs?
So I think that if your reservoirs are unfractured and you don't have significant heterogeneities in your reservoirs, that meaning you can identify an REV. If you can identify an REV, then you can potentially use homogenization techniques and effective property generation to create these upscale approximations. But if you cannot identify an REV and you have fractures, and those fractures are increasing in size as a function of your scale, which is what happens frequently, then what we think is the appropriate, or what we think at this time might be the best way forward, is to try to homogenize using effective methodologies some scale of the heterogeneities in your system, whilst still incorporating larger scale heterogeneities and looking at more site-specific effects. So we're basically advocating using numerical methods to do these types of analysis. I mean, if you follow some of our work and in our book as well, we don't only use numerical methods. We try to only use them in those situations where we have found that we can't use analytical methods. Because, so I work closely with Professor Stillman, who is a very involved in the creation and also the validation of analytical methods in this space. And we're always looking at whether the numerical methods are supporting those, whether the observations in the lab are supporting the analytical methods. When can we use them? Can we use the numerical methods to constrain that space? Can we make that space of applicability larger? That's the type of thing we also do a lot. And then use numerical methods for those cases where you can't get through with where you don't have an REV, you have heterogeneities at multiple scales, and so on.
Brilliant. Tim, one of co-presenters, has a question. Maybe Tim, you could just turn on your mic and ask the question.
Yeah. So, hi, Adriana. I've seen a lot of sort of rock tests done where there's CO2 aging and then not CO2 aging, both in the cap rocks and in the reservoir. But there's a huge sort of range of different outcomes from these tests, saying that sometimes it improves, well, it may weaken the rocks or it may make no difference whatsoever. And what I've seen is that a lot of that variability is probably from the test procedures themselves. I just wondered if you had any ideas about what the optimal process should be for doing CO2 aging and testing on these samples.
I would say that that falls out of my expertise.
Okay.
I
that
don't know. I can tell you that numerically speaking, there are pathways to simulate these types of processes. You can do that at multiple scales. You can even do that as molecular dynamics at the nanoscale. You can observe it. So if I had to put my money on it, I would go with methods that rely on observation in situ, like as in micro CT scanning.
Right. Okay.
The type of thing done by Sam Crever and that type of thing. This is where I would put my money on, but it's outside of my expertise.
Okay, thank you.
Okay.
We probably have time for one last question, and Bob, you have another question. I'm not sure I fully get it, so I'm going to unmute you so you can pose the question. You're on. You please ask your question, Bob.
Oh, it was more just another comment on the lab test and the aging. Sort of had the same conclusion. We started off with 30-day, and then we've extended that and stuff. But is it really long enough when you start we're looking at injecting, 20, 30 years? Does it give us a real representation of what's going to happen that we can then put into the models?
Yes, that's right. It's very important. That's why first principle models are so valuable to us. So we are trying to try for the types of physical processes that we can't understand in the lab and we can't observe in the field and so on. We're trying to rely on first principles, numerical simulations that look at the most basic characterization of the system and the most basic relationships between the molecules for molecular dynamics, or observations in CT scanners where you can actually see the pore space changing and then try to replicate that numerically. There are even people at Harriet Watt trying to do this type of thing with AI now, extensively training AI with CT scans and a smaller scale simulations, but so pore scale simulations of the THMC changes to the porous media depending on what fluid you're injecting and what it's interacting with. But you also have other variables in your system, like the biology. So we also don't know what the long-term biological effects will be of these different systems. So for all of the technologies that I mentioned, there is a biological dimension as well. And we know that that also interacts with permeability. So it is facilitated by permeability, and it can change permeability, both reducing or enhancing. So I don't know exactly what the right answer is yet.
Well, thank you for that.